Oh wow, hi. It's me again. Coming to you from beautiful New Orleans, Louisiana, where I am attending a wedding this weekend, and unfortunately, I do not think I will be back in time for class tomorrow, which means you have the um, fortune or disfortune to have this video recording for what will be the first lesson of chapter 12, which is our first foray into functions of several variables. In this first unit of the course, we've been discussing functions with multiple outputs that give us our vector valued functions or parametrized curves in space. We'll now be shifting to the question not of functions of several outputs, but functions of several inputs. So just to zoom out sort of philosophically a little bit and kind of remind us where we've come from and where we're going. So in calculus 1 and 2, we almost exclusively talk about functions with a single input, typically x, and a single output, typically y. Or we might say that these f's map r to r. They take in one real number and they spit out one real number. And in these functions, we tend to have the graphical convention of graphing them where the domain, the inputs, are put on a horizontal axis. We typically call them the x-axis, and of course the outputs are up on the y-axis. And we think of our domain, this is our domain, as taking an input, x, and then the function sort of transforms that input into an output, y, and then the corresponding point, x comma y, or x comma f of x, is plotted above the axis. And then, of course, if I gather all such points, I'm going to create what we call the graph of the function, if I can manage to not keep erasing everything. And so on. So this is where we cut our teeth on calculus. This is where we developed all of our ideas about calculus. Now, in the first unit of multivariable calculus, we started with sort of the easiest place to start doing calculus of several variables, which is where there were several output variables. So rather than one number going in and one number going out, we had in Unit 1, or in this is Chapter 11 of the Larson 6th edition text, we had functions that took in a single variable t and output several variables x, y, and z, right, up to 3, all bundled together into a vector. Or rather, we would say that r, this vector valued function r that we were studying, would take in one real number r, and it would spit out 2 or up to 3 real numbers. So we would say it maps r to r3. The idea here was a little bit different. We had to think slightly differently in that all 3 of my visualizable dimensions, x, y, and z, were all dedicated to output. They were none of the domain was visible here. There's no t-axis, right? So notably, there's no t-axis. So the domain is not visible. Instead, all 3 visualizable dimensions of space were codomain. They were all 3 dimensions were output. So at some given sort of time on the clock, t equals 7, this input gets mapped to some output, x of t, y of t, z of t. So we actually had to do quite a bit of work here in order to sort of figure out what calculus looks like when the domain isn't visible, right? We had to talk about, there's this kinematic idea, velocity, acceleration, and then there was these geometrical ideas, sort of curvature, tangent, normal directions, and we had to kind of tease out how to separate those two things now that the domain was not explicitly visible as part of the portrait. So from one input to one output, to one input to several outputs, The next stop on the train, of course, now is in chapter 12. This is the unit that we are beginning now. And this is, I think, I would say, if you ask most students who have survived multivariable calculus class, it's much of the content from this section that they remember the most. It leaves the most impression because this is where the visuals start to get really impactful. Now we're talking about functions that will take in two values, say x and y, and they'll output a third z. So not one input, many outputs, but many inputs, one output. So this would be a function f that, for instance, would map R2, so it takes in two real numbers and maps it to R. But also in this section, we'll be studying functions, and I'm going to try to keep the convention of a function with two inputs and one output. I'll tend to give the name f. And a function with three inputs and one output, I'll tend to give the name g. I could have a function g that takes in x, y, and z, and spits out a third number, w, a fourth number, w, in which case this g we would say maps R3 to R. So in this case, a function with multiple inputs, all of a sudden I have two inputs, one output, that only adds up to 3. So I can actually do what I'm used to doing in calculus, which is imagining that I have visible in my 3D space is my domain, and it's back down on the bottom again. So this plane down here, the xy plane, this is going to be my domain again. This is back to being my domain. And I'm going to find some input point, xy. And this point is going to be mapped up to a z-coordinate, f of xy. And now I'm going to have some coordinate triple floating here in space, x, comma, y, comma, f of xy. And if I imagine gathering all such points over all possible input points from the xy plane, I'm going to create a surface. There's the nice collection of all these points in 2D space. I'm imagining that every single point down in the xy plane is sending some point vertically straight up to the surface based on whatever f tells it to do. So for example, I don't know what this surface might have been. Maybe this looks to be kind of quadratic in shape. So today we're going to meet some of the fundamental building blocks of these surfaces. So the graph here is a surface. And a lot of the fundamental building blocks that we're going to get to know really well are the quadratic surfaces, sort of the equivalent of a parabola. So I don't know, maybe this surface was something like f of xy equals 9 minus x minus 1 squared plus y minus 2 squared. Maybe that should be a minus. I don't know, just a random example. Of course, the graph here is a surface. The graph is a surface. I'm going to delay the point right now of how to graph a function with 3 inputs and 1 output. We'll get there very soon. But first, let's meet some of the fundamental building blocks, our surfaces. And you already have, is the thing. You've already met some surfaces. So goal for today is meet some surfaces. So surfaces that will be of the form z, a z-coordinate, being written as a function of x and y. And we already met a few of these. So we've met, we know an object such as spheres. We've met spheres. Right, so a sphere is something of the form, say, x squared plus y squared plus z squared equals 1, for instance. This says all points with distance to the origin 1. So we met spheres. This is a surface. This is a surface, but notably, it's not z solved for as a function of x and y. So in this case, and this is notably not a function, notably not a function, because if I imagine drawing this sphere, it would fail the vertical line test. I still have a vertical line test. I can imagine drawing this vertical line, and I can see that it punctures the sphere in two places. So there was some xy coordinate here. There's some xy coordinate, but there is non-unique z. There was two z values corresponding to that x and y coordinate. So, of course, I'm not going to get a function properly until I solve for z. So I could solve for z, and I would get z equals, let's see, I'm going to subtract the x squared and the y squared, and then I'm going to take a square root, and of course, in taking that square root, I'm making the choice between the plus or the minus. Here I've chosen the plus, and this would only salvage, of course, the top half hemisphere. So this now is, here's my xy plane. I have now a top half hemisphere. This is a top half hemisphere. So now, this sort of classic surface, right, this sphere, one of the fundamental building blocks, now I can think of z as a function of x and y. At any input xy, I shoot it up to the surface, and now I'm up here at the point x comma y comma square root of 1 minus x squared minus y squared. We met a lot of a whole family of surfaces that we called cylinders. The whole family of functions that, of surfaces that we called cylinders would be any equation in only two variables. So for instance, classic example would be to just write the equation of a circle. If I just write the equation of a circle, say x squared plus y squared equals 1, the z coordinate does not appear in this equation, so the set of all points that satisfy this equation will be anything sitting above the unit circle. So we just take this unit circle and we extrude it up into the third dimension. This, of course, is a cylinder. This is what you imagine when you think of a cylinder. This is really what we would call a right circular cylinder. But more broadly, a cylinder could be any shape wherein I have only two variables appearing. So I could draw, let's say, I could write the equation z equals x squared. So in the xz plane, I'm imagining drawing this parabola. And since the y-coordinate has no constraint on it, I simply extrude this shape down the y-axis. And we get sort of a taco shell. This is what we call a parabolic cylinder. The parabolic cylinder. It's that parabola in the yz plane just extruded down. So this is a parabolic cylinder. We also have, of course, planes. Yeah, planes. The most fundamental observation in calculus is you zoom in on a graph and it looks like a line. With surfaces, we'll be zooming in on them and observing that they look like planes. So a plane, we talked about a plane having the equation of the form a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. But I can very easily imagine solving for this z. So I solve for this z, and I'll get something of the form ax plus by plus c on the right-hand side, where this c is sort of an amalgamation of all of those constants, the x naught, y naught, z naught. So what does a plane look like? Of course, you already know that a plane is going to be some sort of flat object in 3D space that is defined geometrically by the fact that it has a normal vector. So there's this normal vector n. And this normal vector n, now I can see if I have this plane written sort of in a functional form with z solved on one side of the equation, I can read off the coefficients and I can see that this normal vector has the form minus a minus b comma 1. So if I were to solve the capital A, capital B over to the other side, I could read off those coefficients again. I'd see minus a minus b 1. So let's learn a few tricks for kind of getting our head around what a surface might look like, and then we'll meet the family of quadratic surfaces, and that's sort of the big goal for today. So hopping over here into Desmos 3D, I'm showing you the graph here of some surface, and what you'll see now is an item pool question that will pop up, and I'd like you to sort of tell me which of those equations that I've provided gives the graph of this surface. Okay, so we can see now that this is the surface z, which I'm now giving the name f of xy. F of xy equals cosine of y. So I have a cylinder. This is a weird sinusoidal cylinder. We can see here, of course, that the x-coordinate does not appear in the equation at all. So if I were to stare straight down the x-axis, I would just see the graph of cosine y. Z equals cosine y. And that graph is simply extruded. So that's kind of the verb that I like to use there. It's extruded down the x-axis. Okay, so this is a cylinder. This is exactly what we call a cylinder. We're pretty familiar with cylinders, so I want to get us away from that. Let's add some extra x dependence here to this right-hand side and see how it changes the picture. So what I'm going to graph, and here I'll turn the surface off really quick. I'm going to graph f of xy equals cosine of y minus x. And I want you to pause the video for just a moment and picture, what do you think this will cause? I'm no longer having a cylinder that is just extruded down the x-axis, but rather that graph of cosine of y, I'm now subtracting x. So take a minute, really picture what you think it'll look like. And I'll show it in 5, 4, 3, 2. Okay. So this is the graph of cosine of y minus x. You can see it looks like the same graph from before, but now sort of raked downward. So whereas when I didn't have the minus x, I just had this graph of cosine of y. And if I were to intersect it with the plane x equals a, right, some constant plane x equals a, I just see a bunch of cosine graphs. A bunch of cosine graphs. All the same cosine graph oscillating about 1 and 0. Sorry, 1 and minus 1. But if I subtract the x, all of those intersections with some x equals a plane are the same graph of cosine, but now they're being either shifted up or shifted down. This is what we call a trace. These are called traces. So I'm going to grab a picture of this really quick and bring it over into OneNote for us to annotate a little bit. think I'm going to grab it and put it in one note for us to annotate a little bit. Yes, here it is. So here back in OneNote, this is the surface z equals cosine of y minus x. And here we're intersecting it with this plane in blue that's just some constant, say x equals -1. So of course, what do? I take these two equations to be simultaneous. And I see that the trace, this is what we call the trace, is z equals cosine of y plus 1. And of course, that's what this graph is that I observe along this line of intersection. This curve of intersection is exactly the graph, right? This is exactly the graph of cosine of y, but shifted up by 1. And this is what we call a trace. This is what we call a trace. This is a trace of the surface. So in the trace, I'm imagining taking one of the variables, in this case x, and fixing it to be some constant and asking what shape do I observe? So when I plug in some constant, or I'm just imagine x to be a constant, I see that z equals cosine of y minus x just looks like the graph of cosine of y just shifted up or down by some amount, and that's exactly what I see. I see the graph of cosine of y shifted up and down by a continually varying amount that sort of rakes the surface up in this way. Mr. Rash always, when he does this example, says, you go out and look at the roof of the Watts building, and you'll see that it's this sort of raked cosine shape is exactly what he calls to be the roof of Watts, which I think is a really nice visual. Of course, I can also look at the y traces, so not intersecting with a plane x equals some constant, but intersecting with a plane y equals some constant. So now I'm imagining plugging in y equals 3 or y equals 7 to our function f, and I just see some constant minus x. So of course, what is that? It's just a line. I just see the graph of some line with slope -1. So the traces with y equals some constant are just the graph of minus x plus some constant. So here back in the OneNote, we can see that the traces with y, this is the surface now, say y equals 3, and this is the surface z equals cosine y minus x. If I take them simultaneously, I see that my traces, so my traces look like z equal minus x plus some constant. Of course, that's exactly that shape I see. That gray line of intersection right here is just some line of slope -1. These are traces, and this is a really great way of sort of wrapping your head around what a surface might look like. Okay, so now you will see an item pool question that asks you to identify which of the functions listed, the functions of x and y listed, will produce this surface. So go ahead and take a moment and answer that question. What do you think is going to give us this surface, which has this kind of importantly sort of radially symmetric looking shape? Okay, I'll reveal now. This was the graph of cosine of x squared plus y squared. So importantly, x squared plus y squared, of course, we know is the squared distance to the origin, right? The square distance back to the origin in the xy plane. And whenever we see a function that has this argument, x squared plus y squared, is sort of the only places our variables x and y appear is in this form, x squared plus y squared, we know we're going to get a shape that has some radial symmetry. So another really important example would be the Gaussian, the bivariate Gaussian, e to the minus x squared minus y squared. Oops, if I could get it up in the exponent for us. This is exactly the 2D version of the bell curve. This is the 2D version of the bell curve. And this is a shape that has perfect radial symmetry. Right? I can imagine that if I were to set this equation equal to some constant, so for instance, I were to intersect it with, say maybe z equals a half. The curve of intersection I see here is going to be a perfect circle. It's going to intersect in a perfect circle because this surface has perfect radial symmetry. So let's take the opportunity again to drop this into our OneNote and comment on this radial symmetry. So here, this was the graph of z equals e to the minus x squared minus y squared. And what I observe is that if I were to sort of set this equal to a half, so I want to intersect it with the plane, z equals a half. Here's that curve of intersection. It'd be a perfect circle. And why is that? Because if I were to go ahead and solve, so solve, I'm going to get, let's see, minus x squared minus y squared equals log of a half, or x squared plus y squared equals natural log of 2. So a circle with radius of the square root of the natural log of 2. So every single sort of slice, every z trace, so this is now a z trace, every z trace with this surface would have that perfect circular geometry, which is telling me that this function has radial symmetry. So here's an important note, is that if you ever have a function of x and y, but that function of x and y really just looks like some functional form only ever on x squared plus y squared, then this is going to be a graph with a surface with radial symmetry. So this always gives a surface with radial symmetry. Okay, the very last thing I want to talk about is a sort of a family of surfaces that is sort of, if the plane is the fundamental flat thing that we're always going to be comparing to for functions of several variables, sort of the next order up, of course, are the quadratic surfaces, things that contain variables to a power up to the second degree. And you've already met a few of them. So the quadratic surfaces. The quadratic surfaces are variables with degree up to 2, terms with degree less than or equal to 2. And you've already met a few of these, right? You've met the sphere, x squared plus y squared plus z squared equals 2. Sorry, equals 1. This is the sphere of radius 1 centered at the origin. Of course, I know I can make the radius bigger by changing that 1. I could change the center, right? X minus 2 squared, something like that. That would shift the sphere around. But also in this family, I have the ellipsoids. So if I were to take my x, my y, and my z, and I were to sort of dilate them by some factors a, b, and c, then I would have effectively just a squished sphere. This is an ellipsoid. So some sort of ellipsoidal cross-sections in that direction, ellipsoidal cross-sections in the other direction. So it'd be an ellipsoid. This is a classic quadratic surface. Again, all of the terms appearing of degree 2. So this is a family you've already met. I think one of the most important families, and one of the examples that we're going to just be talking about all the time, one of the most important surfaces for us to study is the paraboloid. the not parabolid, the paraboloid, the paraboloid. So the standard sort of parent function paraboloid is z equals x squared plus y squared. So here's the xy plane, there's the origin, and the paraboloid is going to be a nice big bowl shape. Here's the paraboloid. And of course, I see that all of my traces, if I take some y traces there, where I set the y coordinate to be constant, I'm going to get my y traces look like parabolas. If I take some x traces in this direction, I'm going to see the same thing. I'm going to see some nice parabolas. Nice parabola there. And if I take a z trace, so if I take a z trace, I'm going to see a nice circular cross-section. Right, so if I take z equals constant, then I get x squared plus y squared equals a constant. So I have nice circular z traces. If I were to take x equal constant, I get z equals y squared plus a constant. So nice parabolic traces in that direction. And my y traces, if I take y equal constant, similarly, I get parabolic traces, z equal constant plus x squared. So see, this is a really powerful way of kind of wrangling a surface in your head. What is it going to look like? Look at those, what we're calling traces. Paraboloid, really, really fundamental. Really, really fundamental. Related to the paraboloid is the hyperbolic paraboloid. The hyperbolic paraboloid. And this is where I similarly have z equals a quadratic function of x and y, but the x and y have opposite sign leading coefficients. So I could have, say, should we do x squared minus y squared? So this is what we tend to think of as being a saddle shape. So I'll have sort of upward opening parabolas in one direction, and then downward opening parabolas in the other direction. And altogether, I get this sort of saddle shape. So I have my x traces. If I take x equals a constant, I get these. Oh, I've drawn this backwards. Yeah, I've drawn this backwards. So let's say this is minus x squared plus y squared. So I get some nice upward opening parabolas in one direction. So z equals y squared plus a constant, a nice upward opening parabola. And then I get downward opening parabolas in the other direction. So z equal constant minus x squared. Of course, why am I doing this such a disservice? We should just graph it, shouldn't we? Let's just graph it in Desmos. So z equals x squared minus y squared. Yes. This very classic saddle shape. So it'll be very important. This is a really key example when we come to talk about optimization, finding local minima and local maxima, precisely because this saddle shape will be a trap that we can easily fall into. We might identify this as being this little saddle point in the middle as being a min or a max, but secretly it's neither. It's what we'll call a saddle. So a really iconic, important shape to keep in mind here is the saddle, the hyperbolic paraboloid, the Pringle. And the last family, I can normally do a pretty good job of drawing these. I just forgot to practice. You have to practice a little. The last family is the cone and hyperboloid family. So in this case, in the cone/hyperboloid family, all of the variables are of quadratic order. So z equals x squared plus y squared. This gives us a true cone. This is a double cone. This is the cone. Of course, not a function of x and y. Z is not a function of x and y. Fails the vertical line test pretty miserably, but of course I could solve z equals square root of x squared plus y squared. And now I will have salvaged just the top cone, the top half cone. A true cone is a double cone. That's the top half cone. In the same family, if I start throwing some constants in the mix, we get the hyperboloids. So if I were to take z squared minus 1 equals x squared plus y squared, I can see here the right-hand side, x squared plus y squared, is always positive, whereas the left-hand side, if I'm not careful, if I throw in some very low values of z, I might get a negative, which means the surface sort of fails to be defined for low values of z. And what that means is we end up getting this sort of gap around the origin that creates what we call a hyperboloid of two sheets. So here's the top half hyperboloid. There's the bottom sheet. I call it as a sheet. The bottom sheet of the hyperboloid. And right there, there's the origin. And of course, I can see if I plugged in 0, 0, 0 to this equation, it would not be happy. The origin would not satisfy this equation, so it's not there. The two sheets of this paraboloid avoid the origin. And similarly, if I were to say z squared plus 1 equals x squared plus y squared, this creates what we call a hyperboloid of two sheets. Sorry, a hyperboloid of one sheet. This is the iconic sort of nuclear cooling tower shape. It's actually exactly what that shape is. It's a very stable structure and a very simple one to construct for some sort of odd, interesting geometrical reasons. This is the hyperboloid of one sheet. Hyperboloid of two sheets. Hyperboloid of one sheet. Okay, that takes us through our sort of introduction to surfaces for our study in multivariable calculus. We are talking now about functions that take in several variables and output only one. We already came into this lesson knowing lots of these surfaces. We know the spheres, the cylinders, and the planes. And we equipped ourselves with some tools for studying surfaces more generally, specifically the idea of a trace. If I were to intersect my surface with a really simple plane parallel to one of the coordinate planes, x equals 7, y equals -1, z equals 0, we get what we call a trace, which is a very helpful way of picturing a surface. And then we met all of our quadratic surfaces, all of these surfaces that are polynomial up to order 2 in our variables, the spheres, ellipsoids, paraboloids, hyperbolic paraboloids, hyperboloids, and cones. These are going to be some very fundamental building blocks that we'll think about a lot in our development of the calculus of functions of several variables. So anyway, thank you very much for paying attention to this video. I hope you watched it at least 1.5 speed, and I will see you on Tuesday.